So let's look at the density function of the generalized random variable, generalized Rayleigh random variable. So by generalized Rayleigh, I actually mean this density function. So where x1, x2, x3, etc. xi's are, where xi's are normal with a 0 mean and sigma squared. So in a way, this is the one way you could think of this is the consider a random vector with x1 through xn, and this is the Euclidean norm. Or in the case of 2, we know that if x1 and x2 are independent Gaussian random variables with 0 mean and variance sigma squared, then square root of x1 squared plus x2 squared is Rayleigh. That's why I have decided to call this to be Rayleigh. So this is the problem. x1 through xn all are independent, identically distributed, 0 mean Gaussian random variables with variance, common variance sigma squared. Find the density function of z. In fact, because it is because there are n random variables involved, and we want to one way to do this would be to derive an iterative formula, which is what I'm going to do. So I'm going to call these random variables to be by the same notation. This will be zn minus 1 squared. So in other words, I'm going to write this as zn minus 1 squared plus xn squared. So then we can look at the distribution function of z. So this is by definition zn less than or equal to z. This is by definition zn is zn minus 1 squared plus xn squared less than or equal to z. So this is the same as zn squared plus xn squared is less than or equal to z squared, which is the this area. So we need to integrate the joint density function of these random variables because this is the equation of a circle within the circle with radius z. So this is minus z2 plus z. This is the random variable, let's say zn minus 1. This is xn. Then if their joint density function is, if the joint density function of zn minus 1 and xn, I'm going to use this variables xy. So this is a standard problem. You take a strip like this. Then this point is, remember this radius is z, so this is c squared minus whatever is this distance. Let me call that to be, let's say y, and c squared minus y squared. So this, of course, you can see it's a double integral. The joint density function of zn minus 1 comma xn evaluated at so this is going to be the joint density function. Here y is constant. We are integrating along this direction. So the variable zn minus 1 is represented by x. So this is dx, and dx goes from minus z squared minus y squared to z squared minus y squared. And similarly, the other random variable x, which is represented xn, which is represented by y here, goes from minus z to z. So now, of course, if you take the this is actually derived. This is a standard result, at least for two random variables, and so this formula is there in the book. And consequently, the density function is the derivative of the distribution function. And this you just have to use the chain rule. So the derivative of this, the derivative of the top limit, then substitute. Remember, this is and multiplied by the second variable dy. So wherever y appears, you substitute the limits and minus the derivative of the bottom limit, which is 1, and substitute again for y this quantity. So for example, when you take the derivative of this and substitute for y, that's a 0 because 0 to 0, so there is no contribution. Same thing with the second term. You take the derivative and substitute for y, this will become 0 to 0, so no contribution. So the third term is leave the limits as they are, take the derivative of this with respect to z again. Again, you have to go through this procedure. So the derivative of that quantity, which is z over square root of z squared minus y squared, and then substitute the, so here of course the variable is x, so wherever you see x, you substitute the top limit. So this will be z squared minus y squared comma y plus the derivative of the bottom limit minus the derivative of the bottom limit, which will be minus goes away, so that will give us a term z over square root of z squared minus y squared f zn minus 1 xn, and substitute the bottom limit, which is with a minus sign. And the third term is the derivative of this quantity with respect to c. There is no contribution. So this is the result. Now, because of this cumbersome notation, moreover, notice that these two random variables are independent because this only depends on x1 through xn minus 1. So we can write this as minus z to z, z over square root of z squared minus y squared. So let me just make this notation, fn minus 1 using here. So this is the density function of this random variable, but evaluated at c squared minus y squared multiplied by f of the identical density function, which is f of y or f of xn of y plus, so this is here, plus fn minus 1, but with minus z squared minus y squared fx of n of y dy. But notice that if n is less than 2, this will become f1, which this will be 0 because this is just the density function of the fz, of course, only takes positive values. So for n greater than 2, this is going to be negative. So consequently, when n is greater than 2, we only have one term. In other words, if n is greater than 2, then this will be, for example, f of 2 or f of 3, but all the z, of course, only takes non-negative values. So this term will be 0. So we will be left with just this term. This is when n is greater than 2. For n equal to 2, this is the result is standard, which is actually Rayleigh, but we can use the same formula itself. So let me do it here. For n equal to 2, f2 of z is going to be minus z to z, z over square root of z squared minus y squared, and n equal to 2. So this is a standard result, standard Rayleigh, but I'm going to derive that also. Because n equal to 2, this will be f1, which is just one random variable. So that's the density function of the Gaussian random variable. So Gaussian, this is also Gaussian. Because it is Gaussian, of course, both the terms do matter. So that's going to be fx of square root of z squared minus y z squared. This is same thing, y. This is x1 and this is x2. And plus fx1 minus square root of z squared minus y squared, fx2 of y dy. But these two terms are identical, so we get a 2. So this now reads 2z minus z to z 1 over z squared minus y squared, and this is two random variables. So this is 2 pi sigma squared e raised to minus the square of this, so that's z squared minus y squared plus y squared from here divided by 2 sigma squared dy. So you have 2z over 2 pi sigma squared goes out, e raised to minus c squared over 2. This much goes out. Then you have minus z to c 1 over square root of c squared minus y squared dy. Notice that this is an even function, so this you can write it as 2 times this. So these 2 cancels, there is another 2 here. And then to do the simplification, just to use some simple substitution. For example, if you substitute y equal to z sine theta, this now reads z over pi 2 sigma squared e raised to minus c squared over 2 sigma squared. Now, when y is 0, theta is 0. When y is z, z cancels, you get sine theta equal to 1 or pi by 2. This is 1 over z, c goes outside. 1 minus sine squared is cos squared, so this is cos theta. And the derivative is going to be z cos theta d theta. So this cancels with this. The answer is pi by 2. So the whole thing is pi by 2. So this pi by 2 cancels here. So you get the result to be z over sigma squared e raised to minus z squared by 2 sigma squared for z positive. That's the Rayleigh density function. It looks like this. Now we can use this on here to do the iteration. So for example, f3 would be, so from here, f3 of z, with the 3 random variables would be minus z to z. I'm going to use this term. Z over square root of z squared minus y squared. F2 of square root of z squared minus y squared, and f of y dy. So if I substitute it here, and f2 we have here already, z squared minus, so this is going to be square root of z squared minus y squared over from here. So the variable is going to be replaced. So variable over sigma squared e raised to minus z squared minus y squared over 2 sigma squared. And this is 1 over square root of 2 pi sigma squared e raised to minus y squared by 2 sigma squared dy. So this cancels. And what remains is, so y squared cancels. So let me bring out, so this is 1 over square root of 2 pi sigma cubed. Sigma squared here, 1 sigma here. So sigma cubed, and there is a z goes outside, minus z to z. E raised to so you also have e raised to minus z squared over 2 sigma squared over sigma cubed, then minus z to z. dy, I guess, because all the terms have sort of cancelled. So that's going to be 2z. So the result is going to be 2 over pi z squared over sigma cubed e raised to minus z squared over 2 sigma squared for z positive. So we can use that format and see that in fact fn of z is of this form, some constant multiplied by z n minus 1 sigma n e raised to minus c squared over 2 sigma squared. So you can see the pattern from here. When it is 2, it is z, and this term is e raised to minus z squared over 2 sigma squared. And when it is 3, this is c squared over sigma cubed, and this factor is the same. So the constant they need to be, so here it is going to be zn minus 1 over sigma n e raised to minus sigma squared over c squared. So finally the only job that remains is to figure out the constant, but that's easy to find because the area under the density function is 1. So this is going to be k over sigma n integral 0 to infinity zn minus 1 e raised to minus sigma squared over 2 sigma squared dc should be equal to 1. We can use this identity. So the simplest, the obvious substitution is z squared over 2 sigma squared. We substitute equal to x. So we get z dz equal to sigma squared dx. So this integral now becomes k over sigma n, and the limits are the same, 0 to infinity. And this I am going to write it as in this manner. Because you can also write this as half z over sigma the whole square. And I'm going to write this as c over sigma because we need all right, so this is c to the power sigma n minus 1, and I need a c here, so I'm going to make it n minus 2, then e raised to minus sigma squared over 2 sigma squared. And previously we had sigma n here. So sigma squared is, so I have now z dz over sigma squared. But notice that z dc over sigma squared is dx. So we can write this as integral 0 to infinity so from here z over sigma is 2x to the power half, right? So this is going to be x to the power 2x to the power n minus 2 to the power half e raised to minus x dx, which is 2 to the power, which is 2 to the power n by 2 minus 1 multiplied by k integral 0 to infinity. Then you have x to the power n by 2 minus 1 e raised to minus x dx. But this is the expression for gamma of n by 2. So this whole thing is equal to 1. So from here we have k equal to 1 over gamma n by 2 multiplied by 2 to the power n by 2 minus 1 in general. So let me put all this and gamma n. So gamma n is n minus 1 multiplied by gamma n minus 1. So this is, we have to consider two cases. If n is of the form 2m, and then this is of course n is 2m, so n by 2 is m, and the gamma m is m minus 1 factorial. Otherwise, if n is of the form 2m plus 1, then if we can write this as an iteration, and this will come m minus half multiplied by m minus 3 by 2, etc., up to half, and then gamma half, which is square root of pi. So I'm going to put all this together here. So in summary, if you have what we have shown is, if you have Zn, which is square root of x1 squared plus x2 squared plus etc. xn squared, where xi's are normal random variables with zero mean and unit variance, the density function of this density function is of the form k z n minus 1 over sigma n e raised to minus z squared over 2 sigma squared for z positive, where k is so n, two cases, n equal to 2m, n equal to 2m plus 1, even or odd. So k is 1 over, so n by 2 is going to be m, so this is 2m minus 1 multiplied by gamma of m, which is m minus 1 factorial. So that's easy. And the other case would be n by 2 minus 1. So n by 2 minus 1 is m minus half. So this is going to be 1 over 2 to the power m minus half, then multiplied by m minus half, etc. up to half square root of pi. So for example, so we can check this formula for 2, 3, etc. So then you depend, so for example, F2 would be, F2 of Z would be M is 2. So this is just a 2 and this is N is 2, so M is 1. So here we have 2 raised to 0, which is 1. M minus 1 factorial. So K is 1 for in that case. And so we get Z over sigma squared E raised to minus Z squared over 2 sigma squared. So this is of course a Rayleigh, standard Rayleigh, 2 random variables. Now 3 Rayleigh would be here. We derived it, but we can check it here. So M is 1 because N is 2, N is 3. So M is 1. If M is 1 here, then this is half. And this would be, the first term is going to be half. So it's going to be square root of, so here you have square root of 2. Here you have 1 over 2. That gives you 1 over square root of 2. So that's a square root of 1 over square root of pi by 2 or square root of 2 by pi, then multiplied by Z squared over sigma cubed E raised to minus Z squared over 2 sigma squared, etc. I'll write one more. So F4 would be, for example, Z cubed 2. So N is 4, M is 2. So we have 2 here. M minus 1, 2 minus 1 is 1. So just 2. So essentially everything has this type of shape. And if you have if you have 5 of them, you can just substitute into that formula. This is 2 over 3 square root of pi and 2 pi Z to the power 4 sigma 5 E raised to minus Z squared over 2 sigma squared, etc. So this is the general result. If you have either the L2 norm or the generalized Rayleigh, the interesting thing is the exponential part is the same as if it for the 2 random variables, but the remaining portion, the power keeps increasing and the constant need to be adjusted so that the area under the density function is 1. And the constant is, this constant is given by here.